All right, so we've just done a whole lot of stuff on polar and non-polar molecules, yes? All right, and we've talked about how polar molecules bond with other polar molecules. And we talked about what sort of bonding when a polar mixes with a polar. What's that bonding there? Dipole, or H bonding. And we did a whole section also on what happens when a non-polar molecule comes next to a non-polar molecule. We call that dispersion, okay? And we talked about temperature-induced dipoles. All right, Lewis, need to watch. So we've talked a lot about secondary bonding forces already. We've talked about H bonding, dipole, and dispersion, okay? And this is a precursor to what we're going to look at next. And you do this every day, basically. You typically, have a wash, or you put something in the washing, okay? And the chemistry behind what's happening when you wash your hands, when you wash your clothes, all right? When you hose oil off a driveway using some strong detergent, okay? Or if you're trying to get a stain off something, all that chemistry involves H bonding, dipole, and dispersion, and a combination of those. And all you need to work out is, what am I trying to dissolve? Once I know what I'm trying to dissolve, I just have to go and find the right solvent for it. Okay, so if I'm trying to dissolve an oil or grease, something that's non-polar, from what we know already, what sort of a molecule are you going to go looking for to dissolve that? Ethan, a non-polar molecule, okay? Boom, all right? Because you know that a non-polar molecule can form dispersion forces with another non-polar molecule. So if I have a grease stain, for example, on the driveway, in the car, I might use petrol to dissolve the grease stain. Now, what happens to it then if I dissolve the oil using petrol? Can I actually get rid of it? No, can't get rid of it. All it does, it just disperses it, just moves it, just spreads it around a bit more. Okay? So what I want to do now is work out how is it that if I add another chemical to it, called detergent, okay, that I can add water and I can get a hose and I can spray it off the driveway. Because
the polar of the detergent mixes with the water and the non-polar mixes with the grease.
How did you know that? Excellent, Jack. He's got the idea, right? Now, I've got two structures that I've put onto the board, okay? One is a soap, one is a detergent. The chemistry is exactly the same. They work the same way, okay? We'll talk more about detergents a little bit later. Detergents are actually more effective because this is a stronger polar end and I can modify the end to make a detergent really strong and very powerful, okay? So I can dissolve just about any non-polar compound. All right, the structure. If we look at the structure for soap, all right, and I've drawn it here with a sodium. Now this will be a solid version of soap. We all know what it looks like. Here it is, okay? Here's my Lux soap, all right? So that's what it looks like right now. When I dissolve it into water, water is the key here, I'm getting rid of the sodium, that goes, because it's just going to become Na plus aqueous, and this whole thing now is an ion, and that will turn into an aqueous ion. Just like sodium chloride, this is now floating around in the water. Okay? So it's now free to move. This is a detergent, okay? That detergent would have been attached also to an actual cation, okay? And the cation has been dissolved, but the detergent becomes aqueous. We have to actually dissolve it, although a detergent is normally in liquid form anyway, yeah? Okay? It's already actually to be used as it is, all right? Normally as a sodium or a calcium salt. All right, now, these molecules have got some features that we already know about, I think, as Jack just told us. This part of the molecule is non-polar, as we were just told, okay? This part of the molecule over here is the polar section of the molecule because we can work out if it's actually negative charge, it's a really large charge. It's not like having OH, which is delta negative. This is a full-on negative charge. Okay, a total negative. So we say that this end of the molecule here is hydrophilic. See why in a minute. Okay, what does the word philic mean? Philae is the top of love, but loving. Okay, if something has got philae, it's got a love for something. So that end of the molecule there loves water. Okay, this end of the molecule is hydrophobic, and if you have a phobia about something, you don't want to go near it. Okay, it's a fear of. Now, chemically speaking, you know why does this nonpolar section have no attraction for water at all? Because water's polar. They're complete opposites. Okay? So you've got this long carbon chain, which is nonpolar, and you've got water, which is polar. There's nothing that attracts those two molecules together, or those two polarities together. Absolutely nothing. Same thing with the detergent. This here is the non-polar section of the detergent, and this is the polar or the hydrophilic section of the detergent. Okay? Everyone cool with that? So the first thing is, what does a soap or detergent look like? And I'm just going to simplify it. I'm going to add it to the picture over here in a second. Okay? And we simplify it by this squiggly line. Okay? And that just basically means they are carbon atoms. And then we're going to put a negative charge at the end. Okay? The negative charge meaning this is the strong polar end of the molecule. Everyone got that? Over here, alright, we've simply got a long carbon chain. That's all it is. Okay, a long carbon chain. What polarity is that? Non-polar. Okay? Okay, so here's what actually happens. In order for these things to work, for that to interact with the actual chemical that we're trying to dissolve, the non-polar chain, we have to actually get them, okay, together with water. That's where the water comes in. We need to have a solvent. So what actually happens is this. These non-polar molecules are attracted to this end of the soap or the detergent. Okay? So over time, we end up with all of these non-polar molecules. There's one. And I'm going to actually draw a bit of a weird diagram. There it is there. So this is the non-polar bit of grease. And there's the non-polar part of my soap or detergent. Okay? And of course, this is non-polar. That means I could end up with another non-polar piece of detergent that's going to turn around and keep on bonding with another non-polar grease. I should have used a different colour for that. Alright? But hopefully what you can see is that over time, in the middle, okay, when we let these molecules move, all of the non-polar stuff is going to be attracted towards one another because they are going to undergo dispersion in the middle. Okay? Now here's where an interesting thing happens, because I'm going to actually draw this, okay, in the water. So what actually happens is when I introduce the soap molecule into the water, it is now actually able to become mobile. It's dissolved. Okay? So we're going to have lots and lots of these soap molecules in water. Okay? And if I've got any grease, and it can be on a piece of cloth that you're putting into a laundry, into your washing machine or anything, but you can just be hand washing as well, or you can have grease on your hands, all right? Or it can be grease on a driveway, all right? Doesn't matter where the grease is. It's a non-polar molecule. So I will actually just grab another colour. So what I'll use for the grease, just to highlight it a bit, is I'll say that the grease, and of course the grease is probably going to be sitting together, isn't it? Because it is not going to want to go anywhere near a water. Okay, they're opposite charges. So any grease, whether it is on a cloth, okay, or whether it's on your hands, or whether it's a piece of oil, okay, floating in the water, it is likely going to be in one big blob itself. And if it is oil, by the way, okay, you know that it's going to form a layer over the top, okay, depending on how much oil there is. Now, if it's in a water environment, I come along and I need to agitate it. Then I need to do that because I need to get these molecules to bump into those molecules. If I don't agitate it, it doesn't work very well, okay? So whenever you're washing your hands, you just don't put water on the soap and just go like that, okay? You've got to actually make sure, all right, that the water has got, okay, dissolved soap. There it is, okay? It'll only work if I've got water present in the soap. And you can see, if I leave it in there, okay, the soap over time, it's actually going to dissolve. So it's going to begin to do its work, okay? So all I'm doing is, I'm taking the soap molecules and I'm actually now putting the soap molecules into the water, okay? I'm actually dissolving the soap. Now, I could add to that if I wanted to. It might just be fun. Add a bit of detergent as well, okay? So now I've got, okay, a mix there of these molecules and these molecules floating around. Okay, now, if I had grease, all right, on my hands, all right, I'd put it into here, all right, I need to actually make sure that I've got lots of water over the surface as well. This is what actually happens now when I actually put my hands into the water, okay, if I've got grease, okay, on my hands, or even if there was actually oil in the water and I was trying to dissolve the oil, okay, or disperse an oil slick, or get water off the driveway. It doesn't matter what I'm talking about. The application is the same. Chemistry is the same. So all of these molecules, that is, all of the soap molecules, will eventually line up like this. They will bond nonpolar, nonpolar. Okay, watching. Nonpolar, nonpolar. In the middle, though, of these soap molecules, because these are also nonpolar, we actually are going to have a whole lot of snakes. Well, not really snakes, but we're going to have nonpolar molecules in the middle. Now, here's where it becomes very complex. This structure, okay, that you can look onto in the sector lesson, looks something like this. So you've got all of these soap molecules, and so many of them that eventually they form a structure that is like a sphere, okay? And, okay, if you can imagine, all right, this is being my actual soap structure. On the outside of this, okay, we've actually got all of these negative charges on the outside. Here it is. So they're all on the outside. All right? So everything negative is on the outside of this structure. This structure is actually called a micelle. There's not one of them, okay? There are millions of these things now set up in the water, okay? So the micelle, okay, there it is, all right, is in the water, okay? However, inside the micelle, we've actually trapped the grease, okay? We've actually trapped the grease. Jack?
The bubbles, when you're washing, is that not polar? And when you're washing with heat bubbles, is that not polar?
Yeah, the bubbles have got air in them, okay, but that's another, I'll get to that one later. That's another whole section we'll look at later, okay? Alright, so on the outside then of this molecule, it's all negative. Here it is, okay? So here's my cell, but on the inside of my cell, we've actually got all together in the inside now, we've trapped all of these grease or dirt molecules are on the inside. Can everybody picture that? Here's the best thing I can do in terms of that picture. So here's a micelle, a very magnified micelle, okay? Negative on the outside, trapped in the inside as grease. So that floating in this, if I had grease, there'd be like billions of these things floating around in that solution. Because as soon as I stirred it, all the soap molecules actually bond with one another, okay? And they would form millions of micelles. While they did that, it actually drags, it's going to drag within it, okay? It's going to pull also and attract the grease or the oil, so that the oil is going to be trapped on the inside. Obviously, if you're thinking, okay, outside of a square, all right, I need to have enough water and I have to have enough detergent or grease to counteract the amount of oil. So obviously the more oil I've got, or the more grease, the more detergent I have to use. Or the stronger the detergent. There's two possible scenarios. Joey, is it a pressing question?
How do you get the grease out?
I'm just about to go there now. Okay? This is a micelle. Okay? Now we're going to look at what happens to a micelle now in water, because this is where we use this end of the structure. We've just used this property of the molecule. We've used the nonpolar bonding with nonpolar. We've used dispersion forces to actually attract the grease, and also for one soap or one detergent to attract itself to form a micelle. But as Joe had said, so how do we get rid of it? It's still here. It's just still in the water. Well, the water does this, okay? We know the polarity of a water molecule, and a water molecule is delta negative, delta positive, delta positive. So there's my water molecule. So the water molecule is attracted to the outside of the micelle. Here's another water molecule. Delta negative, delta positive, dot, dot, dot. Eventually, this whole micelle is surrounded by water molecules. Keeps on going. Okay? Now the water forms a secondary bond with a micelle. In other words, the micelle dissolves into the water. So I'll say that again because the concept is advanced, alright? So I have actually made the grease that is non-polar look like a polar molecule. How did I do it? I used a molecule that had properties of being non-polar and polar. And I've caused the non-polar molecule to attract the other non-polar molecule, but when it's done that, it's actually formed a big polar molecule. And I've used the word polar, but it's very, very strong charge on the outside. Alright? Now, water does not know one micelle from another micelle. If water sees something that's got a delta negative charge, or a full negative charge, it just carries out. This is polar, that's negative. I'll rearrange myself so the delta positive can bond with the negative on the micelle. It doesn't know anything, okay? It's just a molecule at the end of the day, and it will operate based on its polarity. So what I've done is this. All these micelles now, because this would originally been a big piece of oil, remembering though that we're not going to get one of these, the whole solution is going to be filled up with these micelle structures everywhere. And eventually, when I agitate, inside of each micelle is where I'm going to dissolve all of that oil and all that grease. So it's a very tricky way, alright, of actually making the grease sort of disappear. Okay? I've actually hidden the grease on the side of another molecule to make the grease look like it's polar, but we know it's not. Okay? There's no way, if I didn't have soap there, or detergent, there's no way I could shake that thing all day, alright, and the grease is not going to dissolve in the water. We know that. They're opposite molecules. So we use this property, the idea of a polar, non-polar structure, we use that to actually trick the water into thinking that it is a polar structure when it's not. Okay? It's the non-polar part of the soap or detergent that's masking the non-polar character, but as it does, it looks polar. So when we actually then take, if this was actually Joab, okay, so if I was washing my lab coat in here, okay, coming off of the lab coat are all of my cells. So they go from here into solution. If this was oil in here, I've dissolved all the oil. It's now in my cell version, okay? So when I tip it down the sink, okay, obviously my cell goes with the water, it's gone. There's no more grease in here anymore. It's gone down the sink with the water, okay? And so I've actually tricked the water into thinking that grease is polar. And as soon as I get rid of the water, okay, all of my cells go down the sink with it.
There might be some in the bottom.
There's a little bit at the bottom there, okay? So that's actually the whole concept of my cells and how soap detergents work is all based on secondary bonding. Okay, any questions on that?
No, sir.
So when you now go to clean your driveway because you've parked your car in the driveway and it's all oil, that's one of the questions in the worksheet you got. You know that there's no point in standing there with a high pressure hose and hosing off the oil, because all you're going to do is move the oil, make it worse. So what are you going to do?
You're going to put it on detergent.
Excellent. So you're going to get a whole pile of detergent on it, maybe a paintbrush or something. You're going to smush it up with lots of detergent, and it can't be just like normal hand cleaner. It's got to be strong detergent. Okay. Would soap work?
Bleach.
No, bleach is a polar solvent, but good thinking. Soap is not going to be a strong enough chemical to dissolve the oil. So lots of strong detergent, scrub it up, add water, it'll dissolve, and you keep on doing that process over and over again.
Anyway.
Easy peasy.
Oh, you want to not clean your dad's car? No.
No, clean the driveway.